collaborators are listed here. What we generically find in astrophysics is that collisionless shocks are invoked in almost any high-energy astrophysics environment, and they are invoked to do many different things for us, and they are invoked so often, in fact, that we may think of them as a kind of a magic thing. It's kind of like a genie that comes out of a bottle and makes all sorts of wonderful things. So when you have this genie, you basically have three wishes, and typically three wishes that astrophysicists have for collisionless shocks are listed here. So you want this genie to accelerate particles, generate magnetic fields if there aren't enough magnetic fields to begin with, and you also want, in many cases, to equilibrate temperatures between electrons and ions. So we invoke this genie and ask him these three wishes, and of course we're kind of greedy, we want also the fourth wish. So while you're doing all of this, why don't you go ahead and make a collisionless shock? So it turns out that this wish actually comes for free. So as you're doing all of these three, the shock actually, all of these three things are actually part of the collisionless shock, as you find out. So what I'm interested in is to understand how this process actually works from first principles. So I like to show this diagram where where I plot different three-letter acronyms for astrophysical objects which exhibit collisionless shocks, and you can nicely put them on a two-parameter plot, where on this axis I'm plotting the forward velocity of the shock, so gamma beta of the shock. Here we have non-relativistic shocks, and here we have relativistic shocks, and on this axis I'm plotting the magnetization, which is just the ratio of magnetic to kinetic energy of the flow. So this ratio around 1 means relatively strongly magnetized flows, and this is the type of flows that you find, say, in the solar system. And then most astrophysical flows have smaller magnetizations, with the potential exception of AGN jets. And as you can see, they span quite a bit of a range in terms of the forward velocity. Okay, so turns out that almost in any corner of this diagram, you manage to accelerate particles. So all of these objects appear to us in the form of... Yeah.
What is PWN?
PWN? Oh, you don't know this. Also wouldn't know. Right, so... Yeah, also wouldn't know. So actually, they are probably the most relativistic flows in the universe. So we infer gamma of 10 to the 6th for the bulk flow in some cases. Okay, so all right, so we see all of these as a synchrotron sources that they must probably accelerate particles. Okay, so what we want to do is to basically deconstruct this genie bottle and try to understand from first principles how these shocks actually function. So in order to do that, we use plasma simulations because the underlying physics is plasma physics of a shock. So we use this particle in cell codes which represent plasma as a lot of macroparticles which have charge, and as they move through the grid they deposit currents, and then as you solve Maxwell's equations you can advance the electromagnetic fields, and then those fields used to move particles around. So that's a self-consistent way of simulating plasma physics. It's also a very expensive way of simulating plasma physics, but it's the one that misses least amount of physics. So at the moment there are, we're using this code called Tristan MP. There are at least 3 other groups that use similar techniques with different codes, and at the moment I'm happy to say that we're more or less agreeing on most of the results. So I'll show you some of this agreement later. Okay, so let's talk a little bit about the fundamental physics of a shock. What do we actually want to do inside of a shock? So the most important thing the shock has to do is it should decelerate a supersonic flow. So one way to decelerate the flow if you don't have collisions per se, if you can't use Coulomb collisions, is to use electromagnetic fields, of course. And if you have enough background magnetic field, you can imagine a shock as a particle going in a electric and magnetic field. So this is the advection upstream of the shock. And then as you go through the shock, the magnetic field gets compressed. The electric field stays the same, so the particle, instead of going in a straight line, starts to go in an E cross B drift orbit, and that slows down the bulk flow. So that essentially makes the mean flow to be slower than it used to be in the upstream. So this is the simplest way you can decelerate the flow. Another way you can decelerate the flow, at least formally, is to say that, let's say I have some particles moving to the right, and I'll have some particles going to the left. So as far as the hydrodynamics is concerned, the mean velocity is just the sum of these two. So the mean velocity is actually smaller than the velocity of particles going to the right? So if the shock manages to reflect some particles back into the upstream, then formally it has done its job. It has decelerated the flow. Although technically, of course, all of these particles are still going at the same velocity they used to. So this is a kind of a lazy shock. So if you don't have enough magnetic field to slow down the flow and go into nice gyro orbit, what you find out that shocks reflect some of the particles into the upstream, and this interaction between the incoming and reflected particles actually can generate instabilities, and those instabilities generate electromagnetic fields, which in themselves deflect particles further. So we find that there are two kinds of shocks. So there are shocks which I call magnetic reflection shocks, where the plasma is slowed down by the compression of the magnetic field. Those look like this, fairly sharp discontinuity going between the upstream and the downstream. And there are also these filamentary shocks when the magnetic field is low enough so that some of the particles can just go back up into the upstream and generate various instabilities as they stream against the incoming flow. So those will look like this. These are filamentary shocks. It turns out that the acceleration properties of these shocks do depend on which magnetization regime you're in, whether it's a filamentary shock or magnetically reflected shocks. Okay, so what we do in simulations, we essentially have a flow which collides with a wall, and that should launch a collisionless shock into this incoming fluid. And sometimes we use no initial magnetic field. So typically for relativistic shocks, I would have something like gamma 15 flow going into the wall, and then it's reflected, and eventually a shock should form. So you will see compression in density and deceleration of the flow. Sometimes we also add the background magnetic field, which then can get refracted in the flow. We can do this in 2D or 3D. So far, I'll show you most of the results in 2 dimensions. I think all of them check out in 3 dimensions as well. We've tried a few limited cases in 3 dimensions. So one parameter of interest that you can parameterize this problem with is the what we call magnetization parameter, sigma. So it's just the ratio of the magnetic energy to the kinetic energy in the flow. And you can phrase it in many different ways. One way is to say that this is the inverse of the Alfvénic Mach number. So the smaller the sigma, the larger the Alfvénic Mach number. Another way to say it is it's the ratio of the cyclotron to plasma frequency times the C over V of the flow. And you can see here that relativistic shocks actually are simpler than non-relativistic shocks. So this parameter is no longer a parameter for relativistic flows, it's always 1. So you can, just dialing the magnetization, you don't have to worry how fast the flow is actually going. Okay, so let me show you some examples. So this is a collision. The flow is colliding with a wall here, and you're seeing a shock propagate to the right. Is there a way to turn it on? Okay, so what you're seeing here, this is the density. So the fluid is initially coming in like this. This is just my injection of the flow that's moving to the right at the speed of light. And you're seeing a compression created here. Compression is propagating to the right at the shock velocity. Here you see the magnetic field energy actually. And in this case, there was no initial magnetic field in the flow. This was sigma equals 0 flow. And what you see is that the magnetic field is actually spontaneously generated, and it's generated in filaments before the shock. So in the upstream, you see these filaments of magnetic field, which then combine together, merge, and as they merge, the shock is actually created. So you can see the compression in the density and the generation of the magnetic energy as it goes through the flow. Now the magnetic field starts to decay after the shock. We'll come back to that later. Okay, so the important features that we see in these unmagnetized simulations is that we have these upstream filaments which then merge together and create the downstream magnetic field. Also, we're seeing some waves that are generated in front of the shock. So these waves are generated by particles returning from the shock and interacting with the upstream. One way to understand how this shock structure works is to look at the phase space. And what you're seeing here is this is the density through the flow, and this is the magnetic energy. And this shows the particle phase space. This is the x direction versus px, or the momentum in the x direction. And what you're seeing here, so this yellow line is the incoming flow. It has negative x momentum. It's moving in that direction. And then this red cloud is the particles returning back from the shock. So this is the hot backflow returning from the downstream to the upstream. And this interaction is what mediates the collision. This interaction is what generates these filaments. So what makes the filaments is called Weibel instability. It goes back to Weibel in '59, and it was resurrected in astrophysical context by Medvedev and Loeb in '99. And what you see here, I mean, the simplest way to demonstrate it, you have these particles, let's say electrons going to the left, electrons going to the right, and two colliding flows, and then imagining a small transverse fluctuation of the magnetic field will deflect the electrons in such a way as to create the currents. So there will be more electrons going to the left in this region. That would make a current going in that direction. That current is what's producing the magnetic field to begin with. It gets amplified, and this is the recipe for an instability. It's fairly short wavelengths, so it grows on the skin depths of the flow, and the time of growth is just the plasma oscillation time. So it's fairly fast and vigorous instability. Okay, so let me this and show you the spectrum. So it turns out that when you do these simulations, you can look at the spectrum downstream from the shock, and what you immediately find is that the spectrum has two main components. So the spectrum has a thermal component, or Maxwellian component, which has a peak at about the gamma factor of the upstream flow. So if, in this case, I was injecting at gamma 15, and the downstream flow has thermalized to Maxwellian with a peak of around gamma 15 here. But you also see a tail. So this tail is well fit by a power law with an exponential cutoff. And this exponential cutoff is actually evolving in time. So this figure shows the time evolution. You can see the earlier and later curves in energy. And what you see is that the cutoff is moving basically linearly with time. And it tries to build out the power law. At least we think. It seems like it tries to build out the power law. So just the exponential cutoff is moving, but this slope is more or less fixed. So what we find is that about 1% or a few percent of particles are injected into this tail. So you measure how many particles are there. And then since they get to a much higher energy than the mean, they actually carry about 10% of the total energy of the flow. So you inject 10% of the flow energy into this non-thermal tail. Mind you that 90% is still in the thermal part. Okay, so this is an important prediction.
So what is the mass ratio?
This is pair plasma. I'm going to show you electron ions later. If you ask how these particles get there, you can trace their orbits. So this is a space-time diagram. So you have particle incoming. This is where the shock sits. So the black lines represent the magnetic energy through the shock. And you can see that the particle comes in and then it bounces back and forth around the shock. And as it does that, the gamma is increasing. So every time it bounces here through the upstream, the gamma is going up. Okay, so this is a nice movie of how this particle actually gets accelerated. So you can see here a trajectory of one particle. The circle represents the gamma of the particle. So the larger the circle, the more energetic the particle is. The gamma is also shown on this plot. And what you see is that as it goes into the downstream, not much happens to its energy. Mainly it's because this simulation is formally done in the downstream frame. But when it goes into the upstream and it gets deflected by these incoming filaments, its gamma is increasing. So every time it gets pushed back into the downstream, it increases its energy. And that's, we think this is what fundamentally is happening here is a Fermi process. So particle bounces around the shock and it can gain energy from the converging flows. Here is another one. Oops, sorry. Here's another one doing essentially the same thing. So about 1% of particles get so lucky as to go across the shock many times. And what's interesting here is why does this actually happen is you can ask how big the fluctuations of the magnetic field are that are needed in order to scatter particles across the shock. And it turns out that formally the perturbation value of the magnetic field is quite large in this unmagnetized case. What I mean by large is it's a ratio of delta B over B, which is the background B. So background B was very small, so any fluctuation of the magnetic field you have is large. These filaments is what you can see that the particle doesn't scatter on one particular filament. It actually cuts through many of them. And this collective interaction with many filaments is what eventually accelerates the highest energy particles. Okay, so one nice thing is that recently this result was confirmed in a independent simulation. So the group of Luis Silva, Sam Martins is first author, where they've done a very similar simulation, except they actually have electron ion shock with mass ratio of 20. And you can see here a spectrum. This is the electron spectrum. Also shows the thermal and the bump. They didn't run it long enough, so the bump is it's still marginal whether you can say this is a power law or not. If they could run it longer, it would build out to a larger tail. And they similarly see these reflections of particles around the shock. Okay, so let me show you a few things with magnetized shock. So this is a 3D simulation of a sigma equals 0 shock, so no magnetic field. In this plane you see magnetic energy, these filaments in front of the shock. This is the shock compression. And this is the density, so in this plane. So you can see the density larger downstream than in the upstream. Okay, now let's add the background magnetic field. So the magnetic field is going to be in the vertical direction. And this is sigma of 10 to the minus 3, so 1%, less than 1% of the flow energy is in the magnetic field. And what you see that the turbulence is fundamentally different. Now the turbulence now looks like pancakes rather than loops of this Weibull instability. So Weibull instability gets perturbed by the background magnetic field, but fundamentally it's still a filamentary shock. Now if you go higher in sigma, this is sigma of 10 to the minus 1, so 10% of energy is in the magnetic field. Here you see that the shock looks quite different. It's a quite sharp transition. This is actually the magnetized shock that's mediated by reflection in the field. So what we find is that this characteristic transition is about 10 to the minus 3. So anything smaller than 10 to the minus 3 gives you filamentary shocks. The more than 10 to the minus 3 gives you these magnetic reflection shocks. Okay, so it turns out that this also affects the acceleration properties. So let me show you how we study the acceleration for magnetized shocks. So what we do here is we add the background magnetic field, And we fixed the strength of the magnetic field such that if the field were perpendicular, we fixed the strength so that the 10% of energy is in the magnetic field. So this is a fairly magnetized shock. It's strong, it's mediated by magnetic reflection mostly, except in very rare cases when you actually align the magnetic field with the direction of the flow. Then it's harder to do the Larmor cycles. But what you see here is we dialed the angle between the flow and the magnetic field. What you see here is the acceleration efficiency. So this is the spectra, downstream spectra, as a function of the angle. So this is 0 degrees, 15 degrees, 30 degrees. So the angle is measured from the normal. So 0 degrees is along the flow. 15 degrees is going like that, and then 30 degrees is sort of like this. So what you see here is that the tail is increasing as you increase the angle, and then suddenly it cuts off and it stops accelerating. So beyond a certain angle, you don't see any acceleration. If you go to 90, it's still the same. So this is a nice thermal downstream, but the tail basically disappears. And the physics of that is that you go from the subluminal shocks to superluminal shocks, so particles trying to escape along the magnetic field line cannot outrun a relativistic shock anymore. So this typical angle that we find is around 34, I think, 32, 34 degrees when measured in the frame of the downstream. When measured in the upstream frame, you have to divide by gamma. So if you were looking from here, and the shock was moving at me with gamma 15, the critical angle with which the magnetic field could be in order to get acceleration is 34 over 15. So it's fairly small. Basically, the field has to be parallel to the direction of the flow. Okay, so what's happening here? Why is this acceleration changing so much? So what we find is that for larger angles, the physics of shock acceleration is now no longer just diffusive shock acceleration. The particles can just go back and forth, but there's also a shock drift acceleration component, meaning that the particle can particle can stay on the shock and accelerate through Larmor cycles. It will accelerate on every Larmor term. So what you see here is gamma as a function of time. This is a 32 degrees, so almost superluminal, but not quite. And the particle is just sitting on the shock. It's not having much excursion around the shock. Here is. This is a trajectory of a particle for 0 degrees, so the magnetic field is basically along this direction, and you can see the particle goes out of the plane like this, and it's diffusing back and forth around the shock. So this case, this is more or less Fermi type acceleration. If you look at the 30 degrees, the magnetic field is sticking out like this, and you see that a particle is sitting on the shock, and every Larmor cycle it crosses the shock and gains energy. So what you see is the shock drift acceleration, so-called. So not every particle can get injected into this. In fact, only a few particles can. But once they get injected into this process, they get quite efficient acceleration. And what's driving this acceleration is the turbulence in front of the shock. So these particles returning from the shock create waves in the upstream, and those waves can inject particles into the acceleration process. Whereas if you look at the superluminal case, so this is again phase space, there is no returning particles in front of the shock, there is no turbulence upstream of the shock, and nothing gets injected into the acceleration. Okay. Let me show you the electron ion case. This is electron ion on magnetized shock. This is, I think this mass ratio of 100, but we went all the way up to 1,000. And again, you're seeing the density and the magnetic energy. You can see that the shock takes a bit of time to form, but when it does, it's pretty much the same. So you have this filamentation in the upstream, magnetic energy filaments, but now the scale of these filaments is skin depth of the ions. So now we've gone to larger scale. So it's harder to make these shocks in the simulation, but they still form. So even if you don't have initial magnetic field, eventually the magnetic field is generated due to the streaming instabilities. Okay, so one important thing about these electron ion shocks that we find is that there is a very efficient transfer of energy between ions and electrons in these shocks. So what's shown here is this is the density through the shock, and this is the energy in the ions.
The previous slide in the movie, was that at 2 or 3D?
This was 2D. Yeah. So what you see here is the energy in the flow divided into ions and electrons. So initially all of the energy is in the ions, the electrons are cold, and their difference is mass ratio. And then as you get through the shock, the ions seem to lose energy, and all of that energy goes into the electrons. And by the time you went through the shock, maybe 50% of the ion energy is sitting in the electrons. So what we find is there is very efficient electron heating that happens here. And if you have a relativistic shock, the electrons are roughly the same energy as the ions in the shock. That means that the shock works sort of like a pair shock, because the mass ratio is no longer a determining factor. So both electrons and protons have the same Larmor dynamics. So all of the things we found for pair shocks apply for relativistic electron ion shocks. So one interesting thing about this heating, so what's actually causing this, this heating in the flow? What we think is happening is a combination of several effects. One of which is the fact that the filaments in the upstream are driven by ions, and electrons are initially much less energetic, so they're effectively attracted by the ion filaments, and they oscillate around the ion filaments. This was a process proposed by Hededal et al. So electrons go in and out of these filaments, and they can get energy as they go into the filament. They're attracted to the opposite charge, but of course they lose energy as they go out of the filament. So they kind of oscillate back and forth. So I think what's happening to create effective heating is phase-space mixing in the ion filament. So what's shown here is a piece of a periodic simulation. So I have electron-ion flow going one way and electron-ion flow going another way. So this is a periodic simulation. And what you see here is the magnetic energy and the ion density. And then this is going to show you the temperature of electrons in the flow. And what you see is, you can see so in the ion density, you see some filaments going to the right and some filaments going to the left. And the filaments become unstable. So as they become unstable, there is a lot of small subfilamentary structures that are moving left and right over here. And the electrons are kind of feeling these potential wells of the ion filaments, and they go in and out. But on the time scale of going in and out, the filaments change themselves. So there are these substructures moving through the filaments, and that's what's stirring the electrons up. And eventually their temperature is increasing. So what you see here, the red line is the temperature of the electrons as a function of time. As this Weibull instability is proceeding in ions, it seems to deposit quite a bit of energy into the electrons. Okay, so what about acceleration? So electron-ion unmagnetized shocks show basically the same thing as we saw before. So this is the spectrum of the ions downstream. Sorry, this is actually sigma equals 0, so there is no magnetic field here. So this is the downstream thermal, and this is the power law that starts to develop. Electrons also show a power law. By the end of the simulation, so about 30 to 50% of the ion energy went into the thermal part of the electrons. About 5% of energy went into the electron tail. The slope of electrons is about -2 in this case, and about -3 for the ions. But I think this electron-ion simulations are still evolving in time. So I don't think we've reached the convergence in the acceleration case.
What fraction of the energy did the ion tail get?
The ion tail actually got a lot. So ion tail got maybe 15%. So it's quite impressive actually.
Slope is steep, you said, so most of the energy is in the larger ions.
Yes. Yes. So you can see that it attaches to the Maxwellian very, very close to the peak. Right. So it would be interesting to see how this develops further. I don't think we've reached saturation yet. So just to show you, this line would indicate where the ions, so the gamma of the flow times the mass ratio would be. So the electrons are almost close to the equipartition. Okay. This is the electron-ion magnetized case, and what you see here is evolution with angle of the magnetic field to the direction of the flow. So we still see this superluminal effect. So 0, 15, 30 degrees produces nice tails, but then as you go beyond that, the tail basically cuts off, and if you go to 90 degrees, almost no tail is present. So electron-ion shocks still show the same thing. Now, what we find is the ion tail, maybe 25% goes into the tail by energy. The electron tail, maybe from 2 to 10%, depending on what the angle is. So the efficiency of electron acceleration is smaller than ion acceleration, but it's still appreciable. Okay, let's see. I'm 1 minute over. Okay, so. Let me perhaps let me skip the magnetic field amplification and talk about the main conclusions here. So what we find is in this diagram of shock velocities and magnetizations, we find that it's fairly easy to get Fermi acceleration in weakly magnetized environments. So if your sigma is fairly low and you're relativistic, you can get nice Fermi acceleration. If your magnetic field is appreciable, so sigma maybe 10 to minus 3 or above, then you have to be careful about your angle of the magnetic field. So you want to be parallel to the direction of the flow if you want to see acceleration. But in all cases, you have rather efficient energy transfer between ions and electrons. So the thing that we're still working on is understanding these non-relativistic shocks. I hope it's a mess. So what we find when we see nice acceleration in the relativistic case, we start to decrease the gamma factor, and all of the nice acceleration seems to disappear. So we're still trying to understand why this is happening. I think the non-relativistic flows will take much longer to accelerate because it goes like v squared, v over c squared. So maybe it's just a question of waiting long enough. Also, the other types of acceleration are important. So the shock drift acceleration is quite important in injecting particles in the non-relativistic case. Yeah.
So if this is the reason, you can artificially inject some high-energy particles and see if they continue to. I mean, if this is the VRC problem, just
Well, right. So the problem is that you have. I mean, they need self-consistent turbulence. So I can inject by hand, but then they have to proliferate the turbulence. I would have to inject the turbulence also by hand. Okay, so just to conclude, there are following implications of this work for the observations. First, if you at the moment, I think if you have relativistic shocks and you see particle acceleration in the relativistic shocks, I would claim that the field has to be relatively low. So you have to find regions of small sigma in order to accelerate particles, or if you have appreciable sigma, you better be subluminal. So the field has to be aligned with the flow. I don't see any way around it right now. So this, for pulsar wind nebulae, maybe this is a good example where this can actually work. So the magnetization in the equator could be relatively low judging from the simulations that Sergei showed, this is basically the region where you may have reconnection between oppositely directed polarities. And that's probably the region where the magnetization could be relatively low, and that could give you acceleration. Now, in AGN jets, that's a puzzle. I mean, we see these nice data on the toroidal or helical field, but we don't really know where acceleration is happening. Maybe it's happening in the sheath where the field is aligned almost along the jet. Finally, another prediction of this model, natural thing that these shocks seem to produce is, in addition to the power law, they also produce a thermal component. And where this thermal component is in the data is an interesting question. I think most of the time we're not looking for it. We don't have the right tools to fit the spectra. We were not thinking about fitting the thermal component. Everything fits nicely with power laws. But so what we've done with Dimitrios, he presented about this a few days ago in the program. So we just simply calculated what would be the afterglow time evolution light curve if you had a spectrum that had a thermal component and a non-thermal tail. Depending on the acceleration efficiency, you can get sharp turnovers in the light curve. So as your peak of the spectrum is moving through a band, this would synchrotron spectrum would represent here a peak, and then you would have a sharp fall off as you're falling down the Maxwellian, and then you would switch to a power law, and this would represent a shift in the light curves. So we think that this actually explains some of the data seen in Swift, such as the evolution of the spectral index in the Swift afterglow. So this is a paper by Zhang et al., where they show the light curve and then the spectral index component, which seems to show this characteristic transition between soft, hard, and soft evolution. Actually, that are hard, soft, and hard. Yes. Okay, so that's it. We've another thing is potentially we may be looking for evolution of the maximum energy as a function of time is important. So as this acceleration process proceeds, if you just created a shock, the maximum energy may not be what you would expect it to be. So it may actually evolve in time. So looking for that in data could be interesting. So we've replaced this genie with a simulation. So now we can have shocks coming out of the bottle directly without invoking the genie itself. So that's it.
Thank you, Anatoly, for the nice review. We got time for a few questions.
Anatoly, you showed that, claim that the particle acceleration, the maximum energy, increases linearly with time, roughly.
Mm-hmm.
Is this accompanied by a linear increase in the magnetic field, or for example?
Yes. So initially it doesn't, but eventually the particles actually start to back react on the flow. So the extent of so this is a magnetic field at an early time in the simulation. This is a magnetic field at a later time in the simulation. First of all, you can see that the extent of the precursor is increasing. So the extent of the magnetic region upstream is growing with time, and also we find that the energy in the magnetic field is increasing with time, and we've nailed it to correspond to the back reaction of the accelerated particles onto the upstream. So if we turn off the accelerated particles, this growth of the energy is disappearing. And then what's interesting is that this growth of the magnetic field upstream actually persists in the downstream. So this is the early time curve in the downstream, and this is the later time curve in the downstream. So we think that this back reaction can actually sustain maybe 1% magnetic field by energy in the downstream over in the relativistic shock.
So you mentioned at the end that comparing with spectrum, that the peak energy evolves in time. And so, can you remind again how it was? The peak energy increases in time, and then there's something else?
Well, at the moment, all I'm seeing is that the spectrum is pretty much the same, but the upper cutoff is moving in time. Yeah, that's what I mean. So the highest energy is evolving. Now, if you just had a shock form, you may be able to see this in the data, if the time scale will cooperate.
Amir.
So it seems that there's another conclusion you did not stress, and that the acceleration time is much longer than at least commonly thought until now. And that gives you stringent constraint on maximum cutoff energies.
Well, so what you're thinking about is, so I think the acceleration time is still comparable to the Larmor time, right? It's just the question is what kind of field do you pick. So the typical bounds here, it's one Larmor gyration, right? So the typical acceleration time you would take is just Bohm diffusion or Larmor time. But the question is what field do you take, right? These particles sample a larger variation in fields, and the highest energy particles may be actually trying to go through the lowest magnetic field. So that may have a nonlinear effect. But formally, there's still, the time is what you expect.
Since we are talking about time all the time, can you give us a feeling about what are the units of time that
Sure.
are relevant here?
Right. So
how much time does this
Right.
simulation correspond
Right.
to in a realistic case?
right. So this is so everything is dimensional here. So this is 10,000 electron plasma times. Okay. So which depend on the density. Okay. And the magnetic field that we generate here at the peak is about 10% of the kinetic energy of the flow. Okay, so but then the acceleration time depends on which field the particle is actually sampling, which could be much less than 10%. So the field over here and over there is much weaker than what it is at the peak. So that gives you a certain nonlinearity, but I mean, it's obvious. It's fairly short on the GRB time scale. I mean, what you're seeing right
because
now.
if it is short, then we don't have to worry about all this evolution that you're talking about, and maybe there is enough time that if we continue this further, the thermal field that you have will gradually shift more and more energy into the tape.
So we do see the shift of the thermal component.
You see the building up of the tape. So how do you know that over longer time scale, more and more energy is not going into the tail and this thermal structure disappears?
Well, it has to be there to provide the shock. So you can't make a shock just with a relativistic particle.
Well, it's relativistic already. Even the thermal shock is relativistic. Even the thermal component is relativistic because KT is above the ground.
Yeah, but much higher than so these particles are much higher than the cutoff, right? So you're right. I mean, it is an important effect. We do see we do see shift of the spectrum with time. Sorry, I don't know if you can see it here. Probably not. So yeah, I think so. The earlier time is blue curve over here, and the later time is the red curve. So the peak of the thermal does shift in time. It's just conservation of energy because I'm putting 10% of energy over here. So whether this can go to another factor of 10, I really doubt it. So maybe another factor of 2, but it's already 10% here. So I can go maybe to 50%, but I don't think I can put 99% here and 1% in this.
Well, what's the slope?
Where?
In this component, the power?
This 2.4.
So you know exactly, I mean, if you extrapolate it, unless it gets flat. I mean, if you extrapolate it, you know exactly how much energy you're going to have in this component.
Yeah, but this does not contribute energy. This contributes energy.
Right.
I mean, it's larger than 2 spectrum.
Right.
I think we have to stop here. Thanks, Anatoliy.